examine the function g of x equals 2x squared over x squared minus 1 for the following properties and use that info to sketch a graph. We'll start with the domain. This is a rational function, so for the domain we have to see which x values make the denominator equal to 0. If we set x squared minus 1 equal to 0, the x values that will cause that to be 0 are going to be positive 1 and negative 1. So the domain is going to be all real numbers except negative 1 and 1. So that's from negative infinity to negative 1, union negative 1 to 1, union 1 to infinity, if we want to write that in interval notation. So that is the domain. The intercepts, well, the y-intercept is what we get when we set x equal to 0. And when we do that, the numerator is 0, the denominator is negative 1. 0 divided by negative 1 is 0. So the y-intercept is going to be 0, 0. That is also an x-intercept. If we want to find x-intercepts, remember that's when the numerator equals 0, and that's only going to happen when x equals 0. So this is going to be the only intercept for this function. For symmetry, if we look at g of x, if we plug in negative x instead of positive x, squaring x is going to get rid of that negative, and so we would notice that g of negative x is equal to g of x. That means it's an even function, and that means we have symmetry about the y-axis. Symmetry about y-axis. All right. For asymptotes, we will have vertical asymptotes when the denominator is equal to 0. And we already saw that that was when x equals 1 or negative 1. So we have vertical asymptotes at x equals negative 1 and x equals positive 1. For a horizontal asymptote, if we look at the degrees of the numerator and denominator, those are equal to each other, so we will have a horizontal asymptote. And we get that by looking at the ratio of the leading coefficients. That's going to be 2 over 1, which is 2. So we have a horizontal asymptote at y equals 2. All right. Let's keep going. For intervals of increase and decrease, we need to know what the derivative is. And so we need f prime of x. Again, we're going to use the quotient rule. We've got low d high. That's going to be x squared minus 1 times the derivative of the top, which is 4x, minus high d low. That's going to be 2x squared times the derivative of the lower function, which is 2x, all over low squared, x squared minus 1 squared. If we do the multiplications in the top, that's going to give us 4x cubed minus 4x, and then minus, that's also going to be 4x cubed, all over x squared minus 1 quantity squared. That's going to give us some cancellation in the numerator, and this is going to leave us with negative 4x over x squared minus 1 squared. Now we need to find our critical numbers. This function is going to be equal to 0 when the numerator is equal to 0, and that's going to be when x equals 0. So we've got a critical number at 0. And then this derivative is undefined when the denominator is equal to 0. And we already know from the original function, even though this denominator is squared, that we're going to have a 0 at negative 1 and positive 1. So there's going to be 3 critical numbers here, 0, negative 1, and positive 1. So let's go and put those on a number line, and we can start making a sign chart. We've got negative 4x, and we've got x squared minus 1 quantity squared. Negative 4x is going to be positive when x is negative, and negative when x is positive. That negative out front flips the signs. And then this one is, because it's something squared, it's never going to be negative. So it's going to be positive on all of these intervals. And of course, it's 0 in a couple of places. But on the intervals, outside of those critical numbers, it's always going to be positive. And then so we have our derivative down here, and that's going to be positive, positive, negative, negative. So we're going to be increasing, increasing, decreasing, decreasing. And so we're only going to have one local maximum in the middle at 0. And we already know that that is going to be at 0, 0, because we've already figured out that the function value at 0 is equal to 0. I also am realizing, again, I've been using f instead of g's. My apologies. Please ignore that. We've only got that written a couple of times, so I'm going to go ahead and erase those f's and replace them with g's. And I think we're good to go for that. So we've got our local minimum and maximum values. We need concavity, and for that we need the second derivative. And this is another one where I'm not going to go through and do the calculations. I'm just going to give you the answer. I encourage you to pause the video and try and get that yourself, just to make sure that your differentiation skills are up to par. But we've got 12x squared plus 4 over x squared minus 1 quantity cube. And so if we're looking for places where this is equal to 0, the numerator is always positive, so we don't get any critical numbers there. The denominator, we still are going to have 0 if x is 1 or negative 1. So we still do need to look at a sign chart, and we need to look at what's happening at those places and between them. So our numerator, 12x squared plus 4, is always positive. The denominator, x squared minus 1 cubed. Let's see, if x is, I'm just going to look over here first because positive numbers are easiest. If x is bigger than 1, then x squared is bigger than 1, and then this is positive, and a positive cubed is positive. If x is between negative 1 and 1, for example, if x is 0, this is negative, and a negative cubed is negative. And then if x is less than negative 1, this inner part is again going to be positive, and a positive cubed is positive. So our second derivative is going to be positive, negative, positive. So we've got concave upward, concave downward, and concave upward. And we will have, we won't have inflection points. The concavity changes at negative 1 and 1, but these are actually changing because we've got asymptotes. So no points of concavity, but we do have some changes of concavity in those different places. So let's get some axes and start graphing this. Okay, so we said we had vertical asymptotes at negative 1 and positive 1. So let's draw those in. We also had a horizontal asymptote at y equals 2. So something like that. And then we did have one point to plot. We had, it was both an intercept and it was a local maximum at 0, 0. And what did we have about increasing and decreasing and concavity? The function is increasing to the left of 0. So we're increasing, and then we're decreasing to the right of 0. And then the concavity was concave upward on the outsides and downward in the middle. If we look in the middle here, I think we're good to go because this point at the origin is a local maximum, and we know that it's decreasing in concave down to the right and decreasing in concave down to the left. And we've got these asymptotes as guidelines, so I think we're going to have something like this. And the same sort of a thing on the left side. And remember, we did have some symmetry, which matches up. And then we need to see what's happening on the right interval and on the left interval. And if we look at the right interval, we've got this asymptote again. And because it's decreasing and concave up, we know it's going to have to start from up here if it's decreasing, because we can't be decreasing and start from the bottom. So we know it's going to start up here and be decreasing and concave upwards. So it's going to look something like this. It would be nice to pick a point to plot here. So let's actually pick an x value. Let's see what's happening at 2. If we plug in x equals 2 here, we get, I'm just going to do this in some spare space. G of 2 is going to be 2 times 2 squared is 2 times 4, which is 8, over 2 squared is 4 minus 1. So that is 8/3, which is the same as 2 2/3. So that's going to be between 2 and 3, something like this. And because of symmetry, we know that we're going to have a corresponding point at -2, 8/3. And this is just helpful because it gives us a point that we can put to see kind of how closely our graph is going to be hugging on to these lines, these asymptotes. So our graph is going to look something like that with symmetry on both sides. We've got everything that we've calculated represented in this graph, and we're good to go.